Entropy is the measure of the disorder of a system, and it's one of the two things that will determine whether a reaction is spontaneous, happens on its own, or if you have to do something to force that reaction to happen. If I think about a bag of marbles, if that bag were to break, the marbles would scatter all over the place. They would go to a higher disordered state, meaning the entropy would increase. So things like to go from a high order to a very low order. And remember, entropy is the randomness of the system. So it goes from a low entropy, which has high order, to a high entropy, which has low order. So entropy likes to increase. So nature likes to have things happen that are going to increase the disorder of the system. We talked about energy before, and we know that things tend to fall down, not up. So things in nature also like to go to lower energy. This means that a reaction will be spontaneous. It will happen on its own if the energy of the system decreases and the entropy increases. Now, in terms of whether a reaction is endothermic or exothermic, remember you can find that on table I, or you could be given a thermochemical equation that has heat in the equation itself. To determine the entropy, whether the entropy is increasing or decreasing, we need to use a couple of general rules. First, think about the particles in the different states of matter. Solids have those particles really close together, have a very high orderly arrangement in a regular geometric pattern. It has a very low randomness because those particles are so arranged. As it becomes a liquid, the particles start sliding past one another and lose a little bit of that order. So liquids have a higher entropy than solids do. Gases, the particles are flying all over the place. They are completely disordered. So gases have the highest amount of entropy of all of the states of matter. Another thing to keep in mind is dissolved substances are not liquids. We will be talking about things that are dissolved in water. Again, that's something in water. It's not just that substance in liquid form. But in terms of entropy, if I have a solid substance and I dissolve it into water, it's losing that crystal structure and its entropy is increasing as well. Even if the state of matter does not change, the entropy will change as the temperature of your system changes. So as I increase the temperature of a solid, its entropy is increasing. Because those particles are moving faster and faster, there's a little bit more disorder there. It's not as big as when a phase change actually takes place, but it is still changing the entropy. So within a single state of matter, having a higher temperature will also increase the entropy. When you're looking at the energy of the system versus the entropy, whether something's increasing or decreasing in energy and increasing or decreasing in entropy, don't link whether it's endothermic or exothermic with the temperature. Essentially, we're only going to be using the temperature comparison. If I have two samples, one is at 10 degrees Celsius, one's at 15 degrees Celsius, it's the same substance. The one at 15 degrees Celsius would have a higher entropy. The last rule that we're going to use is that if you have more moles, more particles of a substance, it will have greater entropy because there's more ways that those atoms can be arranged. There's more chaos to it because there's more possibilities. If I have all of one type of atom, there's not too many different ways I can arrange that. But once I throw in different types, more atoms, there's a lot more chaos involved in that. When you're looking at a reaction trying to determine whether it is increasing in entropy or decreasing in entropy, look first at the states of matter. If you have solids, liquids, or gases, compare what you have on the reactant side to the product side. If there is a clear change in state of matter, that is going to dictate your entropy change. Only look at the number of molecules if you have all solids on both the reactants and the product side. If you have something where there's solid and gas on one side, but all solid on the other side, you're losing that gas portion and making those gases that were disordered, making them more ordered. So that would be a decrease in entropy, even though you still have solid on the reactant and product side. So look at overall what's happening. If you're getting more gas, your entropy is going to be increasing. If you're getting more solids, your entropy will be decreasing. Again, remember, for a reaction to be spontaneous, entropy should be increasing and energy will be decreasing. It's not just that they're doing opposite things. If entropy is decreasing and energy is increasing, that reaction will definitely not be spontaneous. If they're both increasing or both decreasing, there's some math that gets involved in terms of determining which one outweighs the other. So all we can say at this point would be that we don't know whether it's spontaneous or not.